Alright, 4.4, day 3, the mean and average value theorems. So we've looked at the mean value theorem for derivatives, and that was back in section 3.2. And that said somewhere the derivative of the function was equal to the slope of the line, the secant line, connecting the endpoints of the function. So if we had some function, if we found the slope of the line connecting the endpoints of the function, so we'll call that a to b. It's a continuous and differentiable function. So somewhere there exists some value c between a and b that would have the same slope of the secant line. So the derivative was equal to the slope of the secant line. Now we're going to look at the mean value theorem for integrals. Okay, put this in your notes. But don't worry about the pictures. The pictures are from your textbook. So the mean value theorem for integrals. So check out what this says. If the mean value theorem for derivatives said the derivative was equal to the slope of the secant line, well, think about what the integral shows us. The integral gives us information about the area bounded by a function, the x-axis, and two vertical lines. So the mean value theorem for an integral says somewhere the area of a rectangle is equal to the actual area of the function. So b minus a, that would be our width. F of c, that would be our y value. All right, that would be the height of the rectangle times the width, and this would be the actual area. So in your textbook they give you 3 pictures. All right, so just listen to this. Somewhere the mean value rectangle is between the under approximation. If we were to draw a rectangle that obviously, we're looking at this curve F, under approximated the area, and then the area of this rectangle over approximates the area of the region bounded by the function F. So somewhere between these two values, there's a rectangle whose area is exactly equal to the area under the curve. Alright, so looking at a value, find the value of c guaranteed by the mean value function. So here's my function on the interval from 0 to 2. Alright, so using the mean value theorem, this is what the theorem says. So find the value of c. This is what we're solving for in this problem. So f of c, that would be our function here, just replacing it with c. Oh, let me solve for everything else first. Alright, so f of c times b minus a, 2 minus 0 would give us 2, equals the definite integral. Alright, so let's work on this. The integral from 0 to 2 of 3x squared dx. Using the fundamental theorem, when we take the antiderivative, we have x cubed between 0 and 2. 2 cubed is 8 minus 0. So f of c is equal to 4. Alright, what is f of c? This is where we'll replace in our function. We'll replace the x with the c, dividing by 3. And when we take the square root, we get plus or minus 2 over the square root of 3. But in the given interval, from 0 to 2, we have to eliminate the negative answer. So the value of c guaranteed by the mean value function would be 2 divided by the square root of 3. Alright, now the average value of a function. Okay, put this in your notes, and I'll talk about the picture. So this is what the mean value theorem says. All that the, this should be f of x. Look at what the average value function is. It's just the mean value theorem solved for f of c. So dividing both sides of the mean value theorem by b minus a, we get our average value function. So look at what the average value function gives us. It gives us the height of the mean value rectangle. So where we would draw the rectangle. That information we get from the average value function. So f of c is equal to 1 over b minus a times the definite integral from a to b of f of x. This is a big one. And we'll talk about it more in class, but mean value theorem is where the rectangle intersects the given function. The average value theorem, it gives us the height of the rectangle. So it tells us where to draw it. It doesn't give us any information about where it actually intersects the given function. So average value comes from this function, 1 over b minus a times the definite integral. Where the average value and the function intersect is the information we would get from the mean value. Alright, so using the same function, the average value, that's our average value of a function. So f of c equals 1 over 2, 0 to 2 of 3x squared. We already found this answer to be 8. So, again, what does this mean? The height of the mean value rectangle is 4. Okay, so let's look at this graphically. So the function given was 3x squared on the interval from 0 to 2. So if I look at that, here's 3x squared, and I'm only looking at the right-hand side. Okay, so there's the area of that region. This is my function, 3x squared, bounded between 0 and 2. Okay, so what we just found here, the average value rectangle has a height of 4. So the area of this rectangle, we found this to be 4. So the width is 4, the height of the rectangle is 2. The area of this rectangle is 8. Somewhere there's a rectangle that has an area. The area of this rectangle is 8, equal to the area of the region bounded by the function 3x squared on the interval from 0 to 2. And we know that that's equal to 8 as well. We had to solve that for the average value function. So again, think about what we did with the derivatives. Somewhere the derivative was equal to the slope of the secant line. So the secant line, we could find that slope, change in y over change in x. This is saying somewhere we can find the area of a rectangle to have the same area of a region bounded by some function on a given interval. Now, like I had asked before, where does the mean value rectangle intersect the function? That's the information we get from the mean value theorem, and we already found that. Where does my function intersect the rectangle? And we found that to be 2 root 3. So the mean value theorem gives us where it occurs. The average value theorem gives us the height of the rectangle. Okay, let's look at a couple more examples. So find the average value of the sine function on the interval from 0 to pi. So average value, 1 over b minus a times the integral from a to b of the given function. So 1 over pi, antiderivative of the sine function is negative cosine of theta between 0 and pi. Plugging in the upper bound, we get the opposite of negative 1 minus the opposite of cosine of 0, so that would be 1. So 2 over pi would be the average value of the function. If we think about the graph of the sine function, okay, between 0 and pi, the height of the rectangle, so we're looking at this area, sine function between 0 and pi, the height of the rectangle that we would draw to equal this area would occur at 2 divided by pi. Now this is non-calculator, so I'm not concerned about what that value is. But where does it occur? So find the value of C, guaranteed by the mean value theorem. That's where we would take our function and set it equal to the average value. Now this would be a calculator problem. So try that. Use your calculator and find C. You should get 2 values. Alright, let's do a couple more examples. And this is just another application of the definite integral. Find the average value of 2x cubed minus 3x squared on the interval from -1 to 3. So average value, 1 over b minus a times the integral from a to b of the function. So this would be add 1, divide by the new, add 1, divide by the new. So 1/2 x to the 4 minus x cubed. Okay, so we have 1/2, 3 to the 4th power would be 81, minus 27, minus 1/2 plus 1. Okay, we're gonna have you do that. Use a calculator. Evaluate this function. Alright, let's see this. Find the average value secant squared of x from 0 to pi over 4. Right, average value, 1 over b minus a, integral from a to b. Okay, 1 over pi over 4 is equivalent to 4 over pi. Antiderivative of secant squared is tangent x from 0 to pi over 4. So we have 4 over pi. Tan of pi over 4 is 1, minus tan of 0 is 0. So 4 over pi would be our average value. Okay, and that's it. Check the calendar for homework.